Thank you for the introduction, Ricardo. I'm very glad to be here in Milan, which is actually very close to where I live in Lausanne. It's just 3 hours, 20 minutes by train, so just a quick hop. Great to be in this building, in this room. I really like the logo. Who did the logo? That was a work of brilliance. So great. So let me jump right into my talk, which is about the evolution of Scala, so where it came from, where we're going. So where it came from, well, I'm going to talk about that a little bit, but I want to concentrate on really where it's going. Well, could say, well, is it going anywhere, really? Because you hear a lot that people say, well, Scala is a gateway drug to Haskell. So is it just essentially that we are sort of the sneaky language that essentially will hook people until they are pure functional programmers and become true Haskellists? So maybe we should just recognize this fact and phase out the name Scala. So we actually worked on a different logo again and the design, and we came up with this. So that's also so the designer of that logo is Sandro Stucchi, who is one of my grad students at EPFL. Okay, now seriously, I was joking, of course. Let's talk a little bit of where it came from, and then what I believe are the crucial issues that we have now in Scala and what we want to do with it. So where it came from is I'm sort of a language compiler, guys. Was it essentially all my adult life? I started with Modular 2. That was a language in the 80s. The first thing I did is I wrote a Modular 2 compiler. And the first computer I wanted to write this compiler on was a ZX80. If you remember that the first version of ZX80 had 1 kilobyte of RAM. And then afterwards it got extended to 16 kilobytes or something like that. Well, I gave that up, but I wrote a Modular 2 compiler for the Osborne 1, which had, I think, all of a total of 52 kilobytes of RAM, which was an amazing amount of memory at the time. So after that, I went to Zurich to join Niklaus Wirth, his group, and work with the language, Modular 2, and that during my tenure at Zurich, that became Oberon. So Oberon was the new language. And then afterwards, I fell in love with functional programming, worked a little bit on lambda calculus, Haskell. I was influenced by SML. So all these are sort of influences, early influences to Scala, where we say we want to have something with very good modularity properties that came from Modular 2 and SML, and also, of course, a language that lets you do functional programming in the true sense of the word. So then we're getting closer. In the 90s, mid-90s, I worked on a language called Pizza. That was at the time when Java came out, and we were actually very excited by Java immediately. I think the reason we were excited was, well, Sun backed it. That was a very respectable company at the time. It ran, the promise was it ran everywhere, and it had a garbage collector. And garbage collector was very new at the time, so there were no high-performance languages with garbage collectors at the time. And garbage collection is something that is essential for functional programming. It's very hard to do it without. So we said, well, wouldn't this be a great platform to put our functional programming ideas into? And the first thing I did is I wrote a Java compiler to learn more about Java, so that eventually became JBuilder, the Borland compiler. And then I wrote Pizza, which was sort of our Java++ with 3 functional extensions, algebraic types, pattern matching, and generics. And then the generics got transmorphed into GJ, the generic Java, which became Java 1.4. And so that's sort of my involvement with Java came from there. So once that was done, in the end of the 90s, I said, well, let's take a step back and say, well, if we could design a language from scratch but stay interoperable, what would we do? So we wouldn't do Pizza because essentially Java is too constraining. We saw that there are many things that in pure Java are very hard to do. In fact, what we found in Pizza was that there was a sort of a dual mode. You either would program imperatively, or you would program essentially purely with closures and functions and things like that. It was very hard to combine the two. What we wanted to do is a blend that was more smooth between essentially the object world and the functional world. And that led to then functional nets and funnel, which was sort of a more theoretical study and a more pure calculus-like language. It was a minimal language. And then we found out that minimal languages, they're great to study and they're great to define because they're very small and pure and nice. But to actually write code in them is difficult because they rely on a lot of encodings. That means you have to take higher level concepts like classes and pattern matching and yourself compile it down to lower level concepts. And for experts, this gets quickly boring. They have to do the same encodings time and time again. And for newcomers, it gets very confusing because they don't know the concepts, and therefore they get confused and they have a high ramp-up time. So that led then to Scala, where we said, well, we think we can do a practical combination of object-oriented and functional programming, and let's demonstrate that that's possible. So first there was an experiment we think we can do, and then let's see how that works out. So compared to what we did before, we didn't do concurrency. Concurrency was relegated to the libraries because we found out by then that there's no one true way to do concurrencies. The toolbox is just too big. You don't want to prematurely put that in the language and freeze it. And we had to give up the tight connection between the language and the core calculus. And that's something I regret until now a little bit, but it was sort of necessary to make advances in the language. So what I would hope in the future is that we can regain that really tight connection between theory and language, because theory can feed into essentially a right language design. So it can really guide that. And that's something that we sort of pushed the language a little bit too far out. An example of a language that shows beautifully that you can combine theory and language is SML, standard ML, which is a fairly simple language, tightly connected to theory, but then very few people are using it. So I think in the actual use case, you need to push your language out more towards the applications, and even if that means that you lose a little bit the connection to the calculus. But it's not something that is... it's something that we should try hard to minimize if we can. Okay, what we added in Scala then was a new object and class model, which in fact is more object-oriented than Java's, Java interop and XML literals. XML literals, oh my God, people say nowadays, how could you have added XML literals? That's really the most kitchen sinky thing to do to a language. Why did we do it? Well, what I wanted to have in Scala is I wanted it to have a hipster syntax. Well, at the time, one would have said cool syntax. So I wanted it to have a cool syntax. And at the time, everybody used brackets for arrays, so that was boring. So we decided, well, we use parents instead, right? And then everybody used angle brackets for types. So we said, no, we want to be different. We use brackets for types. But then we needed to find another use of the angle brackets. So there you go. Well, I won't go to the real reason. I think that was iterated long enough. Okay, so what makes Scala Scala? So I think the important ingredients which together make Scala what it is it's a functional language. It's also an object-oriented language. Nowadays, I prefer to say it's a modular language because that sort of emphasizes more what the objects really are good for, and also tells that it's a little bit different from, let's say, mainstream object-oriented languages like, let's say, Java or C#, which have essentially one particular and rather weak object model. It's statically typed. That's very important. Types are foremost, so that's essentially the most important part of the language design, and it's strict. So it's a strict language by default. It has some lazy elements, but it's a strict functional language. So if you compare that to other languages out there, then you could say, well, actually the closest one is probably OCaml and F#, because F# didn't come wasn't before Scala, so it was sort of a contemporary language. So indeed there were a lot of influences from OCaml. The main difference, as I see it, is, except for syntax, is that in OCaml the module system and the object system are different. So OCaml has a very refined and elaborate module system, and then there's also a system of object and classes, and people typically choose one or the other. Actually, most people choose the module system, not the class system. Whereas in Scala, we made a very conscious effort to unify them. So objects are modules, and that's why you have weird constructs, well, weird in quote, scare quotes, that you have essentially objects that have types as members. So you say, well, no other object-oriented language has objects that has types as language. Where does that come from? Well, it came from the modules, because these modular languages, SML, OCaml, they had exactly the same thing. They had modules that had types as members, and that's something that gives you a lot of modeling power. So that's where it came from. The other big difference is that OCaml uses Hindley-Milner, which is essentially a very powerful way of type inference that works very well for a restricted set of languages, whereas Scala uses local type inference, which is necessary because Scala has subtyping in the language. Subtyping is essentially this principle that you can widen a type to its supertype. And a lot of the functional people say, well, do away with subtyping, then we can get better type inference. But what people don't mention then usually is that once you go to modules, once you have a module system, like the module system of SML and OCaml, they have subtyping. Essentially, it's impossible to do such, well, not impossible, I should say, but it's, in my mind, rather awkward to do a good module system without some notion of subtyping. They don't call it subtyping, they call it signature subsumption or signature ascription, but it is really subtyping. It means you have a thing that is more specific and that can slot in for the thing that is more general, and that notion is subtyping. And once you have that, you can't really do Hindley-Milner very well anymore, so that's why Scala has a different sort of type inference. Okay, so that's the difference as to what came before. What's particular to Scala? If we want to condense it, I mean, we could talk all day, Scala is this, Scala is that. But if I want to condense it to say, what are the two most important things? Then I would say the first invariant is this scalability, which is even in the name. So what's the philosophy of Scala very much is that we don't want to provide lots of features in the language. And in that sense, XML was really an accident. XML, we shouldn't have done XML, and we will probably drop it, because that's precisely not what the philosophy is. The philosophy is not to give you lots of prepackaged things that you can use in the language, like, let's say, channels or async or whatever. So what we want to do instead is just have a small set of very powerful abstraction capabilities that let library writers do these things themselves. So for instance, Rich Hickey has asked me once, basically not understanding, why don't you put collection literals in the language? Which Clojure did, even though Clojure claims to be minimal, right? And that was precisely the philosophy. No, we don't want to do this because we don't want to essentially put some set of types where we say, well, this is a list, and this is a map, and this is a set, and these are the implementation types. That's precisely the philosophy, to say, well, we give you these prepackaged things, and that's what you use, and when you want to use anything else, then essentially they're second-class citizens because they don't have the nice syntax. So that's precisely un-Scala-like, and that's why we don't have collection literals, and you have to write sequence in parents, or map in parents, or list in parents, which is a very general principle, which of course desugars to just apply methods. So there you have it. It desugars right into the library. So that's, I think, the first principle. And I think overall it has actually worked quite well so far. In particular, it has led to an abundance of very advanced domain-specific libraries. Good examples of that are, for instance, Spark. So you could say Spark is nothing but a domain-specific language for big data computing on top of Scala. So it has, of course, Spark also has a Python front-end now, and a Java front-end, and an SQL front-end. But at the core, it is a thing that is implemented in Scala and that exposes a Scala DSL to the user. And there are lots of others. There's Chisel for hardware. There are lots of database connectors. tortoise, squirrel, or slick. And there are many, many other essentially languages and communities that are in the domains. And that is a challenge because it means that sometimes essentially we as the language designers give up control by giving the power to the library designers to a large part where they will take it. So give you another counterexample. Let's say Go is a language with a philosophy almost extremely opposite of Scala. Go is a language that says, well, I give you a prepackaged set of things and that's what you're going to use, and I'm not going to trust you to use anything else. So generics only apply to channels and lists and maps, and that's it. You won't be able to get any other generic abstraction. Now, I don't want to denigrate that. I just want to say that's the difference. And in some situations, Go might work very well, and I believe the implicit thing in Go is to say, well, I want to essentially enforce uniformity. And Go does that very well because it says, well, you have a fairly limited tool set, and that's what you're going to work with. Whereas in Scala, we have sort of this sort of meta language where you say, I can build a lot of really powerful libraries, but that means we give up control what these are. And implicitly, we trust the users or the library designers to do a good job here. It's a trade-off, and I'm not saying one is better than the other, just want to model out what it is. So I think that's the first thing that Scala is. It's scalable, it's library-oriented, it trusts programmers and library designers to do the right thing, or at least it trusts the community to sort things out. So the second invariant, which is essentially keeps us busy for most of the time, is type systems. So Scala definitely is very much about the types. The types are the most sophisticated parts of the language, the parts where most of the brain power goes into. And the types in Scala are going a little bit a different direction than the types again in the programming language community at large. So here you see a little diagram where you say, well, with types essentially you always trade off safety, how much you can express in types, what will types prevent you to do, with flexibility and ease of use. So it means how flexible can you use these things. You could say, well, if I would have unit-typed languages, so just one type, or dynamically typed languages, it's the same thing, then I trade off safety for flexibility. Or that means types won't give me any safety, everything's compatible with each other. Not to say that there won't be other things for safety. Of course, types are not the only part, but types won't help me for safety. But I'm going to be very flexible. Other languages such as theorem provers, Coq, Agda, they would say, well, types, I want to essentially, once the thing is well typed, I want it to be automatically correct. I want it to essentially conform to my specification. And I give up essentially ease of use to a certain degree. So that's languages that are very safe and not super flexible. And generally, the trend in type systems has been towards more safety. And I think that's a good thing. I mean, we have made amazing progress in, let's say, Idris, Agda, Coq for theorem proving. That's, I think, an exciting new avenue. Most of it is still research, but I think more of it will come in the future. What Scala currently is about is actually a different bulge, you could say. It's not so much pushing the envelope in safety. So I think Scala is sort of at least as safe as most industry standards now, hopefully safer, but it's essentially pushing it in terms of flexibility, where we say, well, we want actually types to get out of your way. We want types not to constrain you too much, not to give you much boilerplate, so we invest heavily in good type inference, in type systems that can let you express things so that users then don't need a lot of type annotations, and furthermore, that things that are sort of obviously should work. So, for instance, again, to give you one example, so what Scala does is this thing that if a result of a method is, let's say, int, but you don't use the int, then it will just drop the int. Java does the same thing, C does the same thing, they all do the same thing, so you just drop the result. That means in type parlance, you have an automatic conversion from int to unit. And that's something where you say, well, that's something that is actually potentially unsafe. So you might have situations where you really want to enforce that this thing has let's say the unsafe thing is you want to have a function and you think that should be the result of the function, but then by accident you do something else, so the result simply gets dropped and you get a surprise. So it would be safer not to have this rule, but that means that you would have to use a lot of boilerplate, in particular with Java libraries, where essentially even the main of system gets, well, a lot of functions return you something, an error code or something like that, which is not unit. And you would have to sort of assign them all to variables and things like that. So that's clearly where we tried our flexibility for safety. What I hope we can do in the future is keep it as flexible, at least, and push the safety angle. So I'm going to talk about that a little bit further in my talk. So let's talk about where we are now, the present. So the present, and it was very rewarding to see that develop over the last 10 years or so, is that we really have a very big and growing ecosystem of stuff that all essentially is written in Scala and starts to work together. So essentially we have a thing that is growing and more interconnected. So there are lots and lots of these modules from my company TypeSafe, as well as many others that are essentially now, you could say, there's developing a true Scala ecosystem, which of course is connected to the Java one, so Java still remains usable as always, and more software modules have dual interfaces, Java interface and Scala interface, but I think there's also this culture that's developing. The other new thing that happens is that the culture is no longer sitting only on JVM. I think we have a very rapidly growing, still small, but rapidly growing ecosystem on Scala.js anymore, as well, sorry. And I think a big part of that is that as of this year, we have a Scala.js that's no longer experimental, that's actually very fast, has great interop with JavaScript libraries, and that I would say is now probably the most practical language from a typed that compiles from a statically typed language into JavaScript. So if you look at all the parameters, how fast it is, how interoperable it is, and things like that, I think I don't know of any other language that actually would beat Scala.js in these parameters. So I'm very pleased and impressed by how that project has progressed. So why the success? So why did it move so fast and so far? Well, part of it is, of course, always people. There's some very talented and good people doing that. In particular, Sebastian Duran and Li Hao Yi, the two main committers to the system, are just fantastic. But I think also because the environment was right for it. Remember when I told you that essentially Scala is a language that is library-oriented, lets you do the right abstractions from the start, and what I didn't say is, well, it also has interoperability built into its genes because it had to interoperate with Java from the start. But the way we interoperated with Java was not that we say, let's take wholesale all the features of Java and put them into Scala and make Scala a Java++. That's not what we did. We said, well, can we have more fundamental abstractions that can take what is in Java and model it as a Scala feature. So one example is in Scala, everything is an object, everything is a method call. So that means in order to make sense of Java integers, primitive types plus is a method call on an object. Or at least that's how the compiler sees it. Afterwards, the backend will compile that back into efficient add instructions, of course. That's how the compiler sees it. But because the compiler sees it that way, there's no fundamental reason why we can't have a different plus on the JavaScript side and essentially dress that up in the same way. We already have this encoding of other features in languages that work well for Java, and it turned out it also works very well for JavaScript. So I think that's why it works. Libraries instead of primitives, flexible type system, and it's geared for interoperability with a host language. Okay. The other thing that I found very pleasing is that I think this is the first year, or maybe for a year or so now, I don't hear anymore Scala sucks because it has terrible IDEs. That was always the objection before. The IDEs are just terrible. And that has gone away. Now people find other reasons why Scala sucks. But it's not the IDEs. And this is great. This is success. That means that we actually made that the IDEs, I mean, people don't rave about the IDEs. They typically don't. IDEs are something you say is terrible. And if you're happy with the IDEs, you're silent and say, well, it works for me, it's okay, right? But I think we have reached that stage in both Eclipse and IntelliJ, and also the independent ones like Ensign, the Scala mode for Emacs, that have reached a level of maturity where there are tools that people can just get on and work with. So that the Scala IDE now in the version 4 has a new debugger, faster builds, and integrated Scala docs, and that's sort of my go-to IDE because that's sort of what I switched to from Emacs a couple of years ago. IntelliJ is essentially also very good. It has one thing I should mention in the IntelliJ thing, it has a really cool implicit tracker. So here's a screenshot of the implicit tracker that says, well, if you have an implicit search that fails, then it will actually give you essentially the search tree, what it tried to do, why it didn't find it, or if it found an implicit, which implicit it found, things like that. For me, the difference between Eclipse and IntelliJ is mostly that Eclipse is connected to the official Scala compiler that does essentially all the analysis work and things like that. That has the advantage that essentially you get it from the source. That means that the compiler, you know that the official Eclipse compiler will agree with the build compiler because it's the same compiler. Whereas IntelliJ has an uphill battle there. They have their own compiler, so essentially they have to duplicate precisely the rules of the type checker of the original compiler. And it speaks to the talent and dedication of the team that they actually got a very credible result. So I think Eclipse is now actually pretty good, but it's an uphill battle. It's a lot of effort to achieve that. On the other hand, IntelliJ essentially works right with their very powerful abstract syntax tree refactoring machinery. So that's unequaled in IntelliJ, and that's why you have much better refactorings in IntelliJ than in Eclipse. In Eclipse, it was sort of an afterthought, and it doesn't work too well. So that's sort of the trade-off is you want essentially very accurate and fast syntax error diagnosis, go to Eclipse. You want powerful refactorings, go to IntelliJ. That's, for me, the two things. Of course, it would be great if we've arrived at an IDE that combined the advantages of both, and that's sort of future work. I think on both sides, people work on actually getting better on where they're currently weak. The other thing that was a big success, I think, is the online courses. So there are currently 2. One is running right now. We're in week 4 of Principles of Reactive Programming. And then the other one is the Functional Programming Principles in Scala. Who has taken one of the other or the other in this room? Yeah, quite a lot. Yeah, okay. So in terms of numbers of inscriptions, it's really impressive. So far, all the courses together. So the thing is outdated. That was before Reactive started to run. So Reactive now is also up here somewhere. Overall, we had more than 400,000 subscriptions of these courses and a 10% success rate, which is actually very, very high for the industry standard. So most courses are 3, 4, maximum 5%. So we had an average of 10%, which means that with 400,000 subscriptions, we have 40,000 people who actually succeeded in a course like that, solved the assignments, solved the exercises, got a certificate. And that's, I think, is pretty significant because, of course, there are lots of others who maybe didn't bother to do all the assignments and still got most of the course, and they are sort of in the number that's not counted here. Okay, so where is Scala going? That's sort of the present. Where do we want to take it? So I think that the first thing that we see is that we see a platform emerging. That we now have essentially the core libraries, more and more, that are universally used or that many people are using. There's starting to be specifications where the specification is there and can be implemented by more than one party. So examples are the SIP15 for futures, which is essentially gives you a common standard for Scala futures that gets then implemented by TypeSafe, by Twitter, by possibly other parties. Reactive streams is one of the new specifications that I believe we will have quite a few parties implementing those. Spores is essentially functions that can be safely transported over the internet. So all these things, this idea that you have specifications and then different implementations, that's sort of an emergence of a mature platform where we say, well, let's think about what we're doing. Let's not just immediately push out code, and let's agree on a common set of standards. We develop a common vocabulary, mostly pioneered by the Reactive Manifesto. And so that means that we see sort of the beginning of a platform, a reactive platform, sort of analogous to what happened in Java EE in the end of the 90s, where you say, well, you have the language, and now you have sort of the ecosystem around the language and the standards around the language. And I think the reactive platform is sort of what that will be. That's sort of what addresses the needs of today rather than J2EE at the end of the 90s. So you could say, okay, if that's a platform, what's its core? If you go back to the J2EE, and you say the core of the platform is really the JDK, right? The Java Development Kit or the Java Virtual Machine. So the Java Virtual Machine, what it is essentially you have the Java compiler, Java C. It compiles sources to class files. And then there's the JDK JIT, the JIT compiler or interpreter that runs these things on whatever native architecture Java runs on. Okay, so what's then the core, what defines, so this is the standards of the Java platform? Well, it's this, it's the class files, right? Because that's the interface between the front end, the Java C compiler, and the back end that actually then runs it. So the class files, if you compile to class files, then you can run anywhere. That's sort of the contract that you have to keep. So class files are good for portability across hardware, across operating systems, interoperability across versions. So that means that you can have later versions, but the later versions of the JIT still have to honor the contracts of the previous class files. It's a fixed thing, so you can essentially compile to one version of the class file and have it run later in newer versions. So Java 1 still runs today. It's a place where optimizations, analysis, instrumentation happens. Of the JIT compilers itself, of course, but also for a lot of add-on tools, let's say code coverage tools, find bugs. Well, find bugs is probably source, but a lot of the analysis tools actually go to the bytecode because they say the bytecode is more stable than Java. The source language. Source language changes every release, but the bytecode is something that's very stable. So you could say, well, what's the analog of the JDK for Scala? And you could say, well, stupid question. Scala, of course, piggybacks on the JDK. So the current picture is this, that you say you have the Scala source and the Scala compiler, Scala C, and it compiles to the same class files. But it has to add something to the class files because for separate compilation, the Scala compiler has to understand what Scala content of another compilation unit is. So it puts that into so-called Scala signatures, which is just an attribute in the Scala class file. And then it uses the JDK kit to produce native codes. So that's sort of was a very convenient picture, but it's not without challenges. So the first challenge we have is binary compatibility, and probably you all have an idea of what that is, and maybe you all were bitten, a lot of you were bitten by that. So the problem with binary compatibility is you compile your thing with one version of Scala and a set of libraries, and then you want to upgrade to a new one, but some of the libraries haven't been upgraded yet. And then you have this clash that you essentially have to upgrade the whole system to the new version or not do it. So why is that a challenge for Scala and not so much for Java? Well, the first thing is that there's a lot of semantic distance between what Scala is and what the class file bytecode is. If you look at Java alone, then that's actually not true. So it's actually fairly trivial to go from Java to JDK bytecodes. And if there's something significantly happens in Java, like lambdas now, then you see that reflected in the bytecodes. Lambdas are a feature of the JDK now. So again, the distance between the language and the bytecode is not that large. Whereas for Scala, of course, because Scala has to be interoperable with many Java libraries, so it can't use the lambdas, and of course Scala is far out there. It has lots of stuff that is not reflected in the JDK. So it has to work much harder, has to do way more transformations to get down to JDK bytecodes. And in those transformations, there's a lot of design decisions that might change. Nobody gets it right the first time. I mean, imagine, let's say, the JIT compilers that match class files, map class files to native code. Imagine you had told them at the end of the 90s, freeze. No more changes because of native code compatibility. You're not allowed to produce any different native code than before because we have to link these things. Would have been terrible. I mean, we would still be stuck with essentially terribly inefficient JIT compilers, and probably all the bugs from then couldn't be fixed and so on. So I think we just have to admit that nobody gets it right, gets everything 100% right each time. So you have to plan for evolution. You have to plan for fixes. You have to plan for essentially that things will change in the future. It's just natural. But now the problem is that many of these changes that we foresee in the compilation pipeline, they are non-local. So essentially there's an implicit contract between, let's say, a client module and a library module that is essentially in the calling interface and the inheritance conventions and so on. So that's the main problem, that as we change, we need to break this contract from time to time. And as libraries change, it's the same thing. Okay, so the other challenge that we have for Scala is that we have to pick the underlying platform. So far that was easy, it was Java. Now the question is, which Java? Because Java 8 has much more capabilities than Java 6. It has great potential for increasing the efficiency of Scala programs because we can use these lambdas. We can save, I think, about at least half of the class file size could be saved by that, just by not having anonymous classes anymore, going directly to lambdas. But of course, when we do that, then we cut off all the people that are still on Java 6. So we have this conundrum to say, well, are we fast or are we inclusive and have everybody bringing along? And there's no good answer to that. So our answer right now is to say, well, there's two versions of Scala, 1 to 12. There will be Java 8 only. And there's another version, the current 2.11 version will continue to run on Java 6 and 7. And what we pledge to do is that we will keep 2.11 and 2.12 in sync for quite a while. That we say, well, 2.12 will evolve, but we will also have essentially a longer evolution and maintenance interval for 2.11 to essentially take the people who are still on Java 6 with us. But it's a lot of work for the Scala team. It's a lot of effort to be able to do that, and it's also very constraining. You can't move as fast as you want on the 2.12 thing because you still have to be backwards compatible with the 2.11. Okay, so all that said led me to think, or a group of us to think about, well, can't we do something that attacks all these things at once and sort of cut the Gordian knot here? And we came up with something we call Tasty, which is essentially a Scala-specific platform. Tasty is an acronym for Typed Abstract Syntax Trees. So the idea there is that we would have a different format, higher level format in which Scala C would compile, and then that format would be the common format for different platforms. So there could be backends for Java 8, there will be a backend for Java 8, there will be a backend for JavaScript, there could be a backend for Java 6 if that's still important at the time this will all be in production. And the idea then is that the interoperability of Scala code would be assured by this thing. That would be a format that is very close to source Scala, so that means no problems in changing the compilation pipeline because that all will happen after the common format. And the idea then is that our build tool, or rather packaging tool, linker tool that will be in your build chain, it will automatically adapt your tasty trees into essentially whatever platform you have. And it will do the same thing for your libraries. So you can then automatically bring across essentially whole hierarchies of libraries to a new version because they would all be rewritten transparently by that tool. So previously I was just speculating about that, and now I'm very happy to say this thing is actually running. So we have this in production in a compiler. We have verified that we can actually dump things into Tasty, read it out again, and run the backend of the compiler on the Tasty trees, and it compiles exactly as before. So we have demonstrated that this is possible. We have also demonstrated that it is actually quite efficient, that these Tasty trees can be very compact. So what do these trees look like? So an abstract syntax tree looks something like that. So here's an expression x plus 2. And that would be the tree that Scala gives you for that. So remember, every binary operation is a method call. So it's an application of a method. The method is called plus here. And the receiver of the call is the x, which is an ident. And the argument of the call is a literal, which is the number 2. And the arguments of a call generally can be more than one. So there's a list in the tree. There's a list, a cons node, which says the first argument is a literal, the number 2, and then the rest of the list is nil. So it has just one argument. And the red thing on the tree is the types. So the black thing would be just the abstract syntax tree that we have. And that's what every compiler likes to have. So compilers have typically a first component, a parser that takes the source, produces something like this, and then comes essentially the typer, type checker, that adds these types to the tree. So that's what we have. That's essentially the typer view of a Scala program. And then now the idea would be that we simply serialize this format. So, well, we take that and we serialize it. And that's this tasty format, which there's a tasty reference manual here that we have out there. You can consult it. And it essentially gives you a precise definition of how that format looks like. Rather than going through the definition again, I show you an example. So that's a slightly larger thing to see you in context. So that's a function plus 2. It takes an x, which is an integer, and gives you x plus 2. So that becomes essentially a node in the format, which is called a def. That's just the compiler internal jargon for a def definition. And its name is plus 2. And then there's a parameter section, and there's a result type section. And then the body is this apply node. And the apply node has essentially a select. And the select goes to the plus, which is encoded. So it's already the bytecode representation $+, and its argument is the constant 2. So it's just what it looks like. And in fact, these things are essentially running bytes. So if you count, it starts at 57 and ends at 81. So it's 82 to 57. That's 25 bytes of the whole thing, which is roughly the same size as the original source expressions. So we are actually, overall, this example was probably not very favorable for the bytecode. Overall, we see that we are at about half the size of source for these trees, which is actually quite respectable, which means that the whole thing is maybe a quarter of the actual class file size. So it's something that we can add to class files without too much of a problem. Initially, I was worried about that. I thought these trees will become huge, but in fact, they don't. And they don't because we have fairly clever ways, first, to make these things very compact, and second, to avoid types. So the types are actually not recorded in all the nodes, but just in the leaves of the tree. When we have the references, then we have to know what we have. And then essentially all the other types are reproduced automatically by a thing called a type assigner. Okay, so what can we do with it? So we can do lots of things with it. We can use this thing for instrumentation. So what I see is essentially new code analysis things like abide in the future probably would work with this format because it tells you everything that you need to know about a Scala program in a very standardized form. Optimizations, so we hope we will have lots of things to announce by the next Scala Days in Amsterdam. Proof of concepts for hopefully quite impressive optimizers that take a whole Scala program and essentially munge it and inline it very aggressively and eliminate the closures and eliminate that code and have something that is quite compact and very, very fast. Code analysis, refactorings, the list goes on. And also, that's where it came from, the original motivation, automated remapping to solve the binary compatibility issues. So that's essentially the tools thing where I think a lot of it in the future will revolve around this tasty thing, and I'm actually quite happy to say, well, we actually have proofs of concepts, and they seem to work as we think they work. They actually seem to work better than we originally thought they would work. The second thing I want to talk about is the language and the foundations. What kind of work do I envision there? So the first is something where, what I would say, connect the dots. So like I said at the beginning, Scala has sort of pushed ahead a little bit where we just essentially did things because we thought they were useful, and the foundations, the actual theory has lagged a little bit behind. So we have been working on that. There's a calculus called DOT, which is a shorthand for dependent object types, and that's been in a couple of conferences, and there's ongoing work to make that simple and make that very Scala-like and at the same time minimal. So we're still working on a fully expressive machine-verified versions. The state of the art in these calculi is if you claim something, you need essentially an automated proof for it because the details are too complicated. So all these things have to be formalized, in our case in Coq, and essentially all the claims we make about this thing, like claims of type soundness, have to have a machine-checked proofs. There's also a compiler which essentially is more faithful to DOT, called .c, which is essentially the compiler that is the experimental lab for future Scala. So that's essentially the compiler where we have something that is cleaner, that is closer to what we have understood to be the theory now, and where we can try out these things for future Scala. And who knows, this might become the compiler for future Scala at some point. So DOT, here's a paper. I won't bore you with that, just to show you what sort of the differences here is in notations. You use a lot of like math font and things like that. And .c is sort of the compiler which cleans up Scala. So the first thing we're going to do is drop a couple of things that we have now realized have probably been bad ideas. The first thing we're going to drop is XML literals. I was already talking about that. So in the future, instead of an XML literal, you write an XML and then a string, and you get essentially the same interpolation as a macro that you get now for the XML literals. And there will be an automatic rewrite tool that takes your old Scala programs and adds these double, triple quotes and the XML around your XML literals. Because of course we can't do these changes anymore with the code bases out there without an automatic rewrite tool. The second thing we handle likewise is procedure syntax. So I think by now the standard idiom in Scala is always write :unit equals, even if the function has a unit result, whereas so far we had essentially specific syntax for it, but it was sort of, it gave you just a different ways of doing things without actually being a real advantage. So we're going to drop it and going to rewrite your existing code to the new style. And then there are a couple of things that are sort of fairly obscure corners of Scala that we also would like to drop. There's a thing called early initializers. Who knows what they are here in this room? Okay, two. Good. One comes from outside. Hi, John. Right. So, okay. So the rest of you can probably safely drop it. So early initializers, essentially it's a way to say, because traits don't have parameters, sometimes when you want to parameterize a trait, what you need to do is you need to override a val in the trait, but the overriding actually happens sort of after the trait is initialized because of the sequence in which things get initialized, and that sometimes is not good enough. You want to do it before, like you would do it with a parameter, and therefore you had the special syntax to override before you initialize the trait. Now we say, well, just let traits have parameters and be done with it. That's probably the more obvious thing. So we're going to do that. The other thing is more simplifications. So we're going to drop complicated existential types. They have been a source of constant trouble as far as I can see, and hopefully you're not using them. So what we will keep is anything that you can actually express with underscores. So these wildcard types, they will work as before. In fact, you will see they work better as before. So they will have less exceptions in the type inference and things like that. But we buy this for the price of saying, if you have truly outrageously complicated existential types that you have to write with some of these for-some thingies, then we can't deal with that anymore. So that will have to be avoided. I should say that these things you can't even use today unless you import language from language import existential types, right? So if you do that now, then I would say have a code review and say whether you can do without. So I think it's a bad idea to have existential types now, and it would be an even worse idea in the future. So higher kinded types are, of course, very useful, and we're going to keep them, but we're going to essentially reinterpret them somewhat. So a higher kind of type like list will become a type with uninstantiated type members. So let me explain that a little bit. So if you have a type like class list and something in there, so one way to see that is to see it as this type here. So to say, well, we will drop type parameters completely, but we will still have them in the source. So you will still write type brackets list, of course. But the question is, what will the compiler do with it? The compiler will immediately translate it to this and say, well, it's a class, and it has now a type field, type, and it will call this list $t because the name here will be mangled. And we'll say there's a private type t, which is this thing here. So you can still use t inside the class list as before. And it's this mangled thing here, which is a type member. So for the usage, nothing changes. But the advantage is that the compiler has one less concept. And furthermore, there's actually a lot of complications where you say, how do type parameters work with subtyping and variance and all this thing? And all of this can be explained quite beautifully by doing this translation. So this is nice because now the compiler knows exactly what it's doing. It's becoming much simpler, and it's also much simpler to explain what happens with type checking and type inference and so on. Okay, so you say, well, yeah, but what about true higher kinded types? So here's one where you can't do that so simply. So you say the type 2 of t is a pair of t and t. So now you have the problem, well, you say, well, pair is a type, but now you have the same t in both positions. So what we do instead is essentially we give you type lambdas. And here again, I show you the encoding of a type lambda. There will be a source syntax as well, where we say a type lambda, that's essentially a function, call it lambda, a type, call it lambda, and it has here is the type argument. That's this abstract type. And then we say the result of this thing is in the apply. That's a pair of twice the type argument. And there are some rules that essentially will, once you apply this to a concrete type, will collapse it to a pair and so on. Okay. So now if you write 2 of string, what you get is this thing here. It will say, well, it's a type 2, and the higher kinded argument is string. So that would still give you this fairly complex expression, the lambda and then the instantiation. But then you say that's sort of our reduction step. Because you now have defined everything, you have defined the argument and the apply, we just project out the apply. So that's what the compiler does, and that's how it rewrites it. Okay, so that's how we deal with essentially simplifications and unifications of these things. So just to get to the other few things that we want to do, we want to introduce type unions and intersections. So the intersections will replace compound types like t with u, And the advantage of that is that we now have potential blow-up in the size of essentially greatest least upper bounds of types, so that can become very complicated. And with unions and intersections, that's actually much, much cleaner. Okay. So the status is that the compiler is close to completion. That's the .c front end, tasty back end. So this essentially this whole pipeline is almost done. So we hope we will be able to announce that by Scala Days Amsterdam. So that essentially it's a new compiler. It goes to the tasty backend, and then it goes to the essentially new Java 8 backend Gen B code. There's the current effort of Scala 11 and 12 that essentially does that. So we share the same backend, the same new backend for Java 8 that's shared by the two. And there's work also has started to go from Scala C to Tasty, so to essentially make this thing here. That work I'm not sure we will have by Amsterdam, but we will probably have soon after. So that's the current status of things. I just want to quickly say what are the plans for explorations once we have this in space, once we have this in place. So the first thing that I want to look at is implicits that compose better than before. So we already have implicit lambdas, so you can write implicit transaction body, and that's a closure, and essentially transaction is implicit in the body. What about if we also allow implicit function types? So the type of this thing would be maybe then the implicit function that goes from a transaction to a result. If we do that, then that gives us a way to abstract over implicits, which we couldn't do before. So before, whenever you had a function that took an implicit, you had to write implicit parameter blah result type equals, and there was no way you could abbreviate that. You had to write that way time and time again for every function you want to add that to. So now we can actually capture that, and we say, well, something is transactional if it has the type implicit transaction to R. And that means that we can now use these types and we can make them compose. Let's say we have another type like IO, and we can write transactional of IO of R. And IO would be another type of these implicits. So by the way that we actually make this thing a first-class type, we can let these things compose, and that gives you great leverage then in the libraries. Okay. So there's only a single rule that we have to add here to make it work, and that rule is that if the expected type of an expression is an implicit function, then the expression is automatically expanded to an implicit closure. So here's what I mean here with that. So let's say you have a function and it has a body, but you really want to say, well, I should run this body as a transaction. And to run it as a transaction, I need a transaction context. And the transaction context should be something implicit that's passed to all the things that need that context. So what I had to do right so far is I had to write function implicit transaction arrow body. So there was no other way to do that. And that's kind of boilerplatey. So that's something that it should sort of work automatically. So now you can do that just by defining the type. You can say the function is a transactional of R. And that means if you write the body, then the implicit will be automatically added with a name that is just an underscore. Yay, another usage for underscore in Scala. No, not really, but it just means I don't bother the name to use the name. Then you could say, well, how do I get to the transaction context if I don't have a name for it? Well, you use implicitly. You say implicitly transaction of R, and that will give you the implicit that you get. So like now, where mostly you get to implicits just by their types. Okay, so the other thing that this might lead to, I believe, is that I would like to see a better treatment of effects. So far, purity in Scala is by convention, not coercion. So that means Scala is a language where people generally write mostly pure programs, I hope. But it's just convention. Nobody enforces it. You can have any side effect everywhere. And we just again, it's a matter of trust. We trust programmers not to do that, and by and large, I think the community is moving there to write programs where you say side effects are liabilities. And I'm certainly not one of those zealots that says no side effect ever. I think sometimes there's a very good usage of a side effect, but you should know what you're doing. So what we would like to do is explore scholarly ways to express these effects of functions. And these effects can be quite varied. So what you want to capture here is mutation. So you change some variables, you do some I/O, you throw an exception, even dereferencing null. I think that would be an effect for us. So all these things we want to capture. And the important thing to observe here is these effects are additive. That means they behave essentially like a set. In particular, they're also commutative, so it doesn't matter whether I first do I/O and then do some mutation, or first mutation and then do I/O. Should be the same thing. And they propagate along the call graph. Okay, so if we had gone the escalator route, then we would have said thou shalt use monads for effects. And in fact, monads are cool. They're used for lots and lots of different things. But I believe effects are actually not one of the things monads are ideal for, even though they're used a lot for them right now. I think monads are good for lots of other things except effects, because monads actually don't commute. So if you have monad A of monad B, it's not the same thing as monad B of monad A. And we just said effects do commute. So algebraically, monads are actually the wrong notions of effects. And in fact, people are realizing that. Oleg Kiselyov has a nice thing about algebraic effects, and there's recent work by Runar that actually puts these things into Scala using a different device called a free monad that can actually compose these things in non-monadic ways. It's confusing. It's a monad that avoids the use of monads. But the general thing is monad transformers, and that's actually not commutative. I tried to wrap my head around monad transformers when they came out, but then it exploded, so I never got too much into that. Okay, so I really should wrap up. I'm almost done. So what I want to just give you a quick glimpse of that is to say, well, instead of using an effect like this, like I would in Java with an annotation or something like that, how about we say, let's stop talking about effects, let's talk about capabilities. So to say, instead of I throw something, I say, well, to function, I need the capability to throw, which of course implicitly says I might throw something, because what would I use the capability for otherwise? A capability is essentially a thing that I get, and it's convenient to get it as an implicit parameter. So I can write the function like this, can throw exceptions. Okay, or what I could do is I could add a type. I could say I have a type throws. Here's the result type, and here's the exception, and that's just an implicit function from can throw to exception. You've seen that thing before, so that was the thing I did at the start, use types for that. And that means that we can actually use essentially a monad-like syntax and abstractions without using monads. Then you could say, well, if you use the syntax, how does it compose? And in fact, we need something else, and that's where union and intersection types come in. But if you put the pieces together, actually, we can come up with something that works quite beautifully for these things. So let me summarize. So Scala, I think, even if we stop doing it now, which we won't, I think it already has its place in history, in that I believe Scala was the language, or was instrumental in establishing functional programming in the mainstream. It also showed that a fusion of object and oriented and functional programming is possible and useful. It promoted the adoption of strong static typing. If you remember, when Scala came out, dynamic languages were all the rage. So essentially Java was dead, and everybody did Ruby and Python and PHP, which are fine languages, but I think Scala sort of led the renaissance of statically typed languages for a while, to say, well, you can actually do types that are helpful and not annoying. And it has lots of enthusiastic users, conference attendees included, and I'm very glad to be here and talk with you after this talk. So despite being 10 years out, it actually has not that many close competitors, even though I see a lot of languages moving into that space. So if you look at recent languages like C#7, or 6 and 7, or Swift, then you could say they all start to resemble more and more like Scala. We have been a pioneer for some while, and it's great to see other languages actually catching up here. So our aims in the future is to make the platform more powerful, the language simpler, and to work on the foundations to get to the essence of Scala. And I hope that we can, as a community, do that together, and looking forward to lots of interactions with many of you. Thank you.